Hello, my name is Kundeep, and I'm going to teach you guys about differential equations. Now, to help me teach differential equations, I'll be using an AP Calculus BC problem from the 2011 free response section. So let's take a look at the problem. It states that at the beginning of a 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of waste stored at the landfill. Planners estimate that that W will satisfy the differential equation dW divided by dt is equal to 1/25 times W minus 300 for the next 20 years. W is measured in tons and T is measured in years from the start of 2010. So let's start off with the first part. Part A asks us to use the line tangent to the graph W at T equals to approximate the amount of solid waste that the landfill has at the end of the first 3 months or the first quarter of the year. So the two goals for this are to first find the tangent line to W at T equals 0, and the second is once we find the tangent line, we need to use that to approximate the waste after 3 months. Before we begin, it's important to note that dW dt is just a notation for the derivative of W with respect to time. So first let's start off with the derivative. It is 1/25 times W minus 300. And since it is the derivative, it provides the instantaneous slope for W at any time. So all we need to do is plug in a 0 for time, and we get 1/25 W of 0 minus 300. Since the W of 0 is 1,400, we can replace that for W of 0, and we get 1/25 times 1,400 minus 300, and we can just subtract those two numbers. 1,400 minus 300 is 1,100, and then we can divide that by 25, so we get 44. Now, to get it into a recognizable tangent form, we can use the point slope form, and that is just simply y minus y1 is equal to m times x minus x1. We plug in the points 0, 1,400, and when we do, we get y minus 1,400 is equal to 44x minus 0. So simply to get y by itself on the left side, we need to add both sides with 1,400, and we have y equals 44x plus 1,400. To accomplish the second goal, all we need to do is plug in a 1/4, and when we do so, we have 44 times 1/4, which is 11, plus 1,400, which is equal to 1,411 tons. Now let's look at part B. It asks us to find the second derivative in terms of W, and once we find the second derivative, we need to determine whether our answer in part A is an underestimate or an overestimate. Now, as the problem asks, there are two goals. The first is to find the second derivative, and secondly, once we find the second derivative, we need to determine whether our approximation was an underestimate or an overestimate. So once again, let's start off with the first derivative, 1 divided by 25 times W minus 300. And then what we can do is to just simplify the derivative, or make it easier. We can distribute 1/25 across W minus 300 to get 1/25 W minus 12. Now, when we take the derivative, 12 just becomes a 0 because the derivative of a constant is 0. And for 1/25 W, we can use the power rule. So the power of W is just 1, so we multiply that with 1/25, and we have W to the 0th power then, which is just 1. Now we can't just simply write down the second derivative as 1/25 because we are taking the derivative with respect to time. So we do need to multiply 1/25 times dW dt. Now once we've done that, we have the second derivative, but to make it a little bit more clear, we can replace dW dt with the equation that we have. So we'd have 1/25 times 1/25 times W minus 300. And when we simplify that, we have 1 divided by 625 times W minus 300. Now, to find the second part, all we need to do is use some logic and the knowledge we have about second derivatives. So the first thing is that W will never be less than 1,400 during the interval of 0, 1/4. And this was just stated in the problem when they said that the graph of W is always increasing. So since it's always increasing, we can determine that the second derivative will always be positive. And since it's always positive, the graph of w itself will be concave up. And since the graph is concave up, that means that our estimate was actually lower than the actual. So let's move on to part C, which asks us to find the particular solution w is equal to w of t to the differential equation dw dt with the initial condition that w of 0 is equal to 1400. Now this only has one goal, and that's just to integrate dw dt in order to find the original function w of t. Now, before we start, it's important to note that since this is a differential equation, we must first separate the variables, and then we can integrate both sides. So let's start off once again with the original derivative, which was 1/25 times w minus 300. And then we can multiply both sides by dt. And when we do that, we have dw is equal to 1/25 times w minus 300 dt. Now to isolate 1/25 dt, all we need to do is divide both sides by w minus 300, and we are left with dw divided by w minus 300 is equal to 1/25 dt. So now that we've separated the variables, we can integrate both sides separately. And when we do that, we can see that the left side is just a du over u, so that's just an ln, and the right side is just a power rule, or a reverse power rule. So what we have on the left side is the ln of w minus 300 is equal to 1/25 t plus c. And I do realize that both sides have a plus c because it is an indefinite integral. But just to simplify things, I've combined those plus c's together and moved them to the right. Now we can raise both sides to the e. So we have e to the ln of w minus 300, and which is equal to e to the 1/25 t plus c. Since the e to the ln cancel, we have w minus 300 is equal to e to the 1/25 t plus c. Then we can add 300 to both sides, and we get w is equal to c times e to the 1/25 t plus 300. So you guys are wondering, like, what voodoo did you just pull off right here? Why is it c times e to the 1/25 t? And I'll explain. So what I did was, and I didn't show this, I did use a rule where you can, when you're adding in the exponent in exponents, you can separate those two and multiply the bases. So what I did was e times e to the 1/25 t times e to the c. And I did this because e to the c is just a really large constant, because it's a constant being raised to a constant. So then what we have is just a constant times e to the 1/25 t. So that's how I got the c there. So now that we've established what the equation is, we just need to find out what c is. And to do so, we can use the initial condition that they gave us, which was w of 0 is equal to c times e to the 0th plus 300. Now e to the 0 is just 1, so we can subtract both sides by 300. And since w of 0 is 1400, we have 1400 minus 300 is equal to c, which means that c is 1100. So w of t is equal to 1100 e to the 1/25 t plus 300. Now, if you remember, this was about a landfill, but there are other really important applications to differential equations. Essentially, anything that involves an exponential growth will usually use differential equations to predict that growth. For example, if we're looking at the population, scientists have been currently using differential equations to determine the rate and the amount of growth for the population. Now, why is this important? Why do we need to use differential equations, and why do we need to use it for the growth and the rate of population? This is important because when we are looking for the growth and the rate for the population, we need to understand how much the population will increase in a certain amount of time, so that we can accumulate the right amount of resources so that we can sustain a healthy and positive life on the earth. Now, since we can predict this to almost near perfect accuracy, we can have a better understanding and a better future, and essentially we can keep our future secure for not only this generation but for future generations. So with this understanding, I hope you can make a difference in the world. Thank you.